Welcome back to Weapon Science. I'm Ethan Walker. Imagine a massive floating time bomb stretching the length of three international football fields, gliding silently across the open ocean. This is an LNG carrier, the most dangerous yet most mathematically precise machine ever engineered by human hands. Today, we are dissecting a high stakes $3.5 billion geopolitical gamble. Qatar has wagered its entire energy future on South Korea's legendary shipbuilders to construct a fleet capable of carrying 260,000 tons of liquefied natural gas. One mistake. And the consequences are catastrophic. Mathematically, the energy density stored within these massive tanks is equivalent to 60 times the explosive force of the Hiroshima atomic bomb. If a breach occurs along global maritime trade routes, it is not merely an economic loss. It is a global thermodynamic disaster. The primary enemy of this vessel is not fire, nor is it the raging ocean waves. It is temperature. To keep natural gas in a liquid state, it must be cooled to an extreme cryogenic threshold of minus 163 degrees Celsius. At this temperature, normal steel shatters like glass. This is a metallurgy challenge of divine proportions, where a single millimeter of structural deflection means total failure. Why did Qatar bypass cheaper alternatives in China and Japan to award this historic contract exclusively to South Korea's big three shipyards? Qatar is pursuing an incredibly ambitious target to scale up its LNG production to 142 million tons per year by 2030. For a project of this magnitude, they do not need cheap ships. They need absolute, uncompromising engineering precision. Logistically, transporting natural gas in its gaseous state over oceans is physically impossible. The volume is simply too vast. To make transport viable, we must compress and shrink its physical scale by an astonishing ratio of 1 to 600. Imagine an entire professional football stadium filled to the brim with natural gas, suddenly compressed until it fits inside a single tiny storage tank on this vessel. That is the extreme level of volumetric energy density we are dealing with. To use an everyday analogy, imagine 600 bottles of mineral water suddenly shrinking and fusing into just one single bottle. This incredible efficiency is the economic cornerstone of Qatar's $35 billion energy export empire. But the open ocean is not a controlled laboratory. When a 300-meter vessel slams into 15-meter waves, it experiences immense kinetic forces. The challenge is keeping the volatile cargo thermally isolated while the ship is violently tossed about. This is where advanced material science comes into play. In metallurgy, we must fight a phenomenon known as low-temperature brittleness or cold brittleness. If you submerge a common rubber band into liquid nitrogen, it loses all elasticity instantly. Upon the slightest tap, the frozen rubber band shatters like delicate glass. Standard structural steel reacts exactly the same way when exposed to cryogenic temperatures of minus 163 degrees. Its molecular structure undergoes a fatal transition. At the atomic level, extreme cold halts the natural vibration of atoms. The metallic bonds become rigid and brittle. Without specialized nickel alloys or advanced membrane structures, the ship's hull would fracture like a dry cracker under the weight of the LNG. This is why South Korea's engineering precision is non-negotiable. Their solution lies in Invar steel, a specialized superalloy containing 36% nickel. This material forms the indestructible backbone of the modern LNG carrier. Without this advanced alloy, Qatar's multi-trillion-dollar cargo would be nothing more than a ticking time bomb waiting for a thermal trigger. The primary weakness of standard steel is its high coefficient of thermal expansion. Think of a cotton shirt that shrinks drastically after being washed in hot water. Normal steel undergoes similar dramatic dimensional changes when exposed to extreme temperature swings, leading to immediate structural tearing. Invar, however, remains virtually static, whether exposed to minus 163 degrees during cargo loading or plus 40 degrees while sailing through tropical waters. This alloy maintains its precise dimensions, preventing catastrophic structural failure. The technical complexity is mind-boggling. These Invar plates are only 0.7 millimeters thick, nearly as thin as a single strand of human hair. Welding these ultra-thin sheets together without a single microscopic gap requires master-level execution. This laser welding precision is comparable to the cleanroom standards of semiconductor manufacturing. It is why South Korea, operating under license from France's GTT, completely dominates this highly specialized maritime sector. With an engineering tolerance limit of just zero point 0.1 millimeters, even the slightest deviation can result in a global disaster. At this level of execution, Qatar does not look for cheap builders. They demand absolute, flawless perfection. In world-class engineering, a single safety barrier is never enough. Directly behind the primary Invar membrane lies a secondary defense barrier constructed from grade 304 stainless steel, creating a redundant, multi-layered shield. This design mirrors the strict containment protocols found in advanced nuclear or semiconductor facilities, ensuring absolutely zero leakage, even if the primary containment layer suffers a highly unlikely localized failure. Look closely at the unique waffle-like geometric pattern stamped into the steel plates. This is not for aesthetics. The geometry is mathematically calculated to distribute mechanical stress evenly across the entire surface rather than letting it concentrate. The greatest mechanical threat to an LNG carrier is a phenomenon known as sloshing. As the ship navigates rough seas, the liquid cargo inside the massive tanks acts like a giant, high-velocity hammer slamming against the interior walls. Without precise structural engineering, this internal liquid hammer would easily tear the ship's hull apart from the inside out. We are talking about a gravity multiplier effect where 1 ton of free-moving liquid generates 2 tons of kinetic impact. Without South Korea's advanced structural calculations, these containment tanks would fail within hours of encountering a major ocean storm. To survive, the walls of the tank must actually be designed to dance in sync with the forces. Much like a flexible accordion, the membrane must expand and contract seamlessly under extreme thermal shock and external wave action. This is the engineering marvel known as the breathing wall, a structure that bends but never breaks. Let's look at the hard comparative statistics. In extreme stress simulations, competing cargo containment systems built by Chinese yards failed after 180,000 pressure cycles. Japanese designs lasted through 300,000. Meanwhile, South Korean hulls easily surpassed 500,000 cycles without showing a single micro defect. This unmatched structural longevity is why Qatar is willing to pay a premium price. They are purchasing absolute operational security. Think of driving a vehicle over a severely damaged road. A cheap suspension system will transmit every violent jolt directly to your spine. But a premium active suspension makes you feel as though you are floating effortlessly over smooth asphalt. A South Korean-built LNG carrier is that premium suspension system. It tames the colossal kinetic energy sloshing within the cargo tanks, ensuring the ship's main hull remains completely unaffected by the violent forces inside. This vessel operates in a state of permanent thermodynamic siege. On the outer deck, the blazing equatorial sun can heat the steel plating up to 40 degrees Celsius. Yet just inches below, the cargo must remain at minus 163. This massive 200-degree thermal gradient is a violent force that would warp and shatter ordinary industrial metals in an instant. The physics are simple. If you bring a glass of ice into a hot desert, it melts in seconds. But inside a high-tech, vacuum-insulated cooler, that same ice can survive for days. The challenge here is scaling that high-tech cooler up to a length of 300 meters and ensuring it functions flawlessly without fail for 30 years. In the LNG industry, any gas that evaporates during transit is lost profit. This natural evaporation process is known as boil-off gas, or BOG. If the insulation system is imperfect, Qatar's valuable cargo literally evaporates into the atmosphere. The superior efficiency of South Korea's insulation systems minimizes this boil-off gas, turning potential multi-million-dollar losses back into pure profit. A mere 1% loss of cargo efficiency equates to over $10 million evaporating. For Qatar, this is not just a minor statistic, it is a critical vulnerability. If boil-off gas is not carefully managed, pressure inside the containment tanks will rise exponentially, transforming the vessel into a massive pressure cooker. To prevent this, South Korea developed a proprietary 5-layer insulation system, essentially a giant high-tech spacesuit designed for a ship. Let's dissect these defensive layers to understand the extreme precision involved. The first defensive barrier is a 270mm layer of ultra-high-density polyurethane foam. This is not ordinary foam. It is a specialized material engineered to block massive thermal transfer from the outside environment. Directly behind this foam lies a second layer of 140mm glass fiber. This layer provides crucial structural integrity, acting as a flexible backbone that prevents the insulation from cracking during violent ocean transits. The third layer utilizes perlite, a naturally occurring volcanic mineral. Its microscopic pores are engineered to trap air molecules, creating a highly stable passive thermal barrier that remains completely unaffected by cryogenic temperatures. The fourth layer features a vacuum insulation panel, the ultimate thermal barrier. By creating a near perfect vacuum, we eliminate the air medium entirely, leaving no path for thermal energy to conduct or radiate into the cargo. This system achieves an incredibly low thermal conductivity rating of just 0.02 watts per meter Kelvin. To put this in perspective, a standard commercial styrofoam cooler is 3 times more thermally leaky than this industrial system. On the global efficiency scoreboard, South Korea leads with an unmatched boil-off rate of just 0.08% per day. Compare this to China's 0.15% and Japan's 0.13%. For Qatar, this tiny fraction of a percent translates directly into billions of dollars saved over the life of the fleet. However, even the most advanced insulation can fail if it suffers from the presence of thermal bridges. Imagine wearing a thick, high-end winter jacket but leaving the main zipper slightly open. The freezing outside air will immediately penetrate that small gap, rendering the rest of the expensive insulation completely useless. To eliminate thermal bridges, South Korea relies on a highly integrated manufacturing ecosystem. Companies like Dongsung Finetech produce these massive insulation panels using advanced vacuum molding to guarantee absolute material density. This seamless integration between high-tech material manufacturers and the world's largest shipyards is a unique industrial advantage that no other nation has been able to replicate at this massive scale. Consider the sheer physical scale. A single LNG containment tank has an internal surface area equivalent to 3 international football fields. Maintaining absolute structural integrity across this vast area is a monumental engineering feat. Precision is the ultimate law in these shipyards. Technicians apply specialized silicon oil sealants to the secondary barrier, using microscopic inspection tools to ensure there is not a single atomic gap in the seals. The quality standards are incredibly strict. The airtightness of the secondary barrier must pass a test threshold of 10 to the minus 6 millibars. This is the exact same airtightness standard that NASA uses for deep space exploration capsules. In the past, maritime operators treated boil-off gas as unavoidable waste, venting it into the atmosphere or burning it off via flare towers. This was the economic equivalent of throwing stacks of cash directly into the ocean. But South Korea changed the game by developing the reliquefaction system. This onboard chemical plant captures the escaping natural gas vapor and instantly cools it back down into its liquid state, returning it directly to the cargo tanks. This system operates on a closed-loop refrigeration cycle. Heavy compressors pressurize the boil-off gas, pass it through advanced heat exchangers, and then expand it rapidly to force the temperature back down below the liquefaction threshold. HD Hyundai has pushed this reliquefaction technology to a historic milestone, achieving an unprecedented efficiency rating of 99%. Virtually every single escaping gas molecule is successfully recaptured. This reduces total cargo loss during long-distance voyages to an astonishingly low 0.03%. This is the absolute physical limit of thermodynamic efficiency allowed by modern materials and technology. Over a 20-year operational lifespan, this single technological innovation saves Qatar an estimated $500 million per vessel. This massive return on investment makes the choice of South Korean shipyards incredibly logical. You might argue that these South Korean vessels carry a massive upfront price tag. That is true, but when you factor in the extreme thermal efficiency, the premium cost is completely recovered within the first 2 years of active operation. In maritime logistics, this is the classic strategy of high capital expenditure yielding extremely low operating expenses. Furthermore, these advanced reliquefaction systems slash the ship's overall carbon footprint by 20%. With the European Union implementing strict carbon taxes on maritime vessels starting in 2025, South Korea's highly efficient ships will receive green lane access, bypassing expensive environmental penalties that competitors will face. This green compliance gives Qatar a massive competitive advantage in the global energy market. Now, let's address the obvious question. Why didn't Qatar choose China's Hudong Zhonghua shipyards, which offer significantly lower prices? For Qatar, the stakes are simply too high to compromise on quality for a discount. Let's look at the critical structural differences. On one side, we have the standard NO96 design. On the other, the advanced Mark III Flex system. South Korean shipbuilders are the absolute masters of optimizing these thermal insulation systems. They don't just build cargo tanks, they construct giant floating, high precision thermodynamic fortresses designed to hold minus 163 degrees. A competitor's vessel with a higher boil off rate of 0.15% results in hundreds of billions of rupiah in lost gas every single year across a large fleet. A cheap initial purchase is a recipe for long term financial bleeding. Qatar understands this engineering reality perfectly. They are not buying a simple transport ship, they are purchasing a 30-year guarantee of uninterrupted, highly profitable, and completely safe maritime operations. But what about Japan? They were once the undisputed kings of the ocean. The answer lies in technological stagnation. Japanese builders like Mitsubishi remained committed to their iconic spherical Moss-type cargo tanks for far too long. While highly reliable, this spherical design suffers from severe volumetric limitations and a high center of gravity. In rough seas, a high center of gravity makes the ship far less stable than South Korea's sleek, low-profile membrane designs. By keeping the cargo's center of gravity incredibly low, South Korean vessels slice through heavy ocean swells with maximum hydrodynamic efficiency. This is why Qatar feels entirely secure placing their multi-billion-dollar assets in Korean hands. Think of playing a game of Tetris. Japan's spherical cargo design is like trying to pack round marbles inside a square shoebox. You end up with a massive amount of wasted, empty space that cannot be utilized for cargo. In contrast, South Korea's membrane technology utilizes up to 95% of the hull's internal volume. In the world of global shipping, this volumetric efficiency is everything because every empty cubic centimeter represents lost revenue. Samsung Heavy Industries didn't just follow existing blueprints. They completely re-engineered stress distribution at the tank corners, where cryogenic pressures are at their absolute peak, minimizing the risk of material fatigue. At Hanwha Ocean, manufacturing precision has reached semiconductor-like cleanroom standards. They utilize advanced robotic systems for the critical welding phases, achieving an incredibly low defect rate of just 0.01%. This level of consistency is physically impossible to achieve through manual human labor. Meanwhile, HD Hyundai has integrated the ship's advanced propulsion systems directly with the cargo management computer, boosting overall efficiency by 8%. This is the ultimate barrier to entry. South Korea is not just selling steel ships, they are selling 30 years of accumulated engineering experience and operational data that cannot be reversed, engineered, or copied overnight. Behind this technology is an unmatched pool of human capital. The master welders in South Korean yards are not mere laborers. They are elite artisans who undergo thousands of hours of training to earn cryogenic certification. Another critical advantage is construction speed. South Korea can complete a massive LNG carrier in just 28 months. Compare this to China's 32 months or Japan's 36. In this business, speed is the ultimate competitive edge. For Qatar, every single day of delay represents a massive financial loss. Their extraction facilities are constantly producing gas. If the ships are not ready at the pier, the resulting opportunity cost is absolutely staggering. Now, South Korea is leading the world into the next frontier, AI-driven autonomous shipping. In 2022, the Prism Courage successfully completed a 20,000-kilometer autonomous voyage across the Pacific Ocean using Level 4 AI navigation. Using the advanced Avikas Hinas system, the ship's AI scans the ocean 360 degrees with radar and LiDAR sensors, optimizing routes in real time to cut fuel consumption by an additional 7%. From Invar steel and 5-layer insulation to AI navigation, South Korea does not just build ships, they engineer the future. I'm Ethan Walker for Weapons Science. Do you think any other nation can ever challenge this level of precision? Let us know in the comments below.